welcome back. We had a not a week off, but a little mini spring break. Hopefully people are somewhat recharged. If you're not recharged by the break, maybe this nice weather will do it. Let's see here. I'm hoping to get your midterms back to you this week. So I'm partway through grading those. So I'll send those back to you as soon as I can via email. Let's see. Yeah, I guess we're just kind of in the middle of it right now. We're talking about how to solve problems using the methods of equilibrium, which is what we're used to. Ideas of balancing the forces. In this case, it's accounting for how stress diverges in a body. And we talked a lot about stress. We talked about the equations of equilibrium, that the divergence of your stress tensor must be balanced by the body forces. If there are no body forces, then your stress and your object should be divergence free. Divergence free is like a fancy way of saying there's no kind of sources or sinks. Like the body is not like kind of holding in stress or kind of exerting stress on its surroundings. To solve problems in solid mechanics, you need equilibrium equations, you need kinematic equations, you need compatibility equations, and you need constitutive equations. We now understand our equilibrium equations. We also understand how to transform stress from one state to the next. And so we move on to the next one, which is our kinematics, or more simply talking about strain. Again, this is one of those things where you've learned about strain before, but now we're going to kind of pull back the curtain and see that it's a little bit more complicated than we had initially encountered. And it's for the same reason. It's the same problem all over again. Mechanics and materials, we tended to just assume that we could average things over our structure. We averaged stress, which meant that our differential equations became algebraic equations. We averaged strain, which meant that our differential equations for strain became algebraic equations for strain. But in a real object, just like stress varies throughout the body, strain varies throughout the body. And if something varies throughout a spatial distance, that property is going to be governed by differential equations. And it's kind of easy to see, or I think it's a little bit easier than stress. You know, if we go back to that beam stretching problem we did a while ago, we had a cantilever beam stuck to the wall and we pulled on it. And we kind of knew, like, okay, well, the end of this beam is stretching a lot. The part touching the wall can't stretch at all. So there must be some sort of way to match those two things. If this thing's stretching a lot and this part's not stretching at all, there's some gradient that's going to happen throughout that object to kind of take us from something that's stretching to something that's not. So you can kind of see, I think, variations in strain a bit more easily. The other thing that we're going to do that's different. So the first thing we're going to do is we're going to derive the differential equations that describe strain in an object. And what those really are just ways of saying, how does displacement change in the X, Y, and Z direction at a point after we kind of stress this object. So that's the first step we're going to do. And it's going to involve us introducing differential equations that describe how the displacements change. It's obvious that it should be, I don't know if it's obvious. It makes sense that it should be a differential equation because displacement could change in X, Y, or Z. And whenever you have to consider a change in something with respect to more than one independent variable, you end up with differential equations. The second thing we're going to do is new. It's also not, it's one of those things that I want you to see, in part because I saw it much later, and I wish I had seen it earlier. And it is the fact that, for most of what we learn in mechanics of materials, and most of what we do in structural mechanics, and even if you go to graduate school and you take a course on elasticity, what you'll find is even at that level, we tend to assume, or we tend to develop the mathematical models for small strains, linear strains, really small deformations. And that's kind of for two reasons. One reason is nonlinear strains or large strains are nonlinear, and we don't really know how to do much with nonlinear things. We can throw them at a computer and have them try to help us solve them, but there's very little we can do with kind of pen and paper. And so nonlinear problems are hard and large strains are nonlinear. The second reason is a bit more historical, which is that if you're primarily engineering things out of steel, bricks, wood, concrete, these things aren't undergoing large deformations. But now we're in a time where we're seeing the benefit of applying principles from mechanics to biological systems where growth is occurring. Small strain doesn't mean anything if you're talking about like how large does the uterus expand during a course of a pregnancy. There's no smallness to that. Small strains don't really have any utility if you're talking about how to make a soft robotic articulating finger, which is going to bend as much as our fingers can bend here. These things are undergoing incredibly large deformations. And we could go on and think about all the applications in which this small strain limit breaks down. Another would be, and this is kind of probably a little early, but I think you're going to see in the next 10 years a rollout of flexible electronics and wearable electronics, and kind of smart bandages that are going to be able to track insulin for you, or monitor your exposure to various toxins, or help you regulate things in your body, or just even trying to generate electricity off of your mechanical motion of you walking around during the day. People have stuck piezos to the bottom of sneakers so that they can generate a tiny amount of electricity that charge something in their backpack by just walking around all day. This wave of kind of flexible, wearable, stretchable electronics is not here yet, but it's coming. And most of these things involve large deformations of complex structures. And so while if you're worried about only, do I need to know these equations to get a good grade in this class? Like, no. But if you're going to go work in a company or go to graduate school, you're going to encounter these terms, and I want you to know what they mean. And I want you to be able to, at the very least, say, oh, wait a minute, okay, I know where to go look up stuff on that. That's different than the small strain stuff. I know there's an extra challenge when it comes to large things, large deformations. I should go and check something. That's kind of what I want you to be aware of. It's just the awareness of that there's a limit to where the kind of simple small strain stuff that we can do pretty easily, there's a limit to where that starts to break down. And we're not ready to be armed with how to tackle all those problems, but we are ready to be exposed to it and kind of be aware of the way that they can complicate things. But let's not get there yet. Let's start simple. We know that stress causes strain. We know that stress causes deformation. Strain is our way of measuring deformation. And we know from mechanics of materials that strain is a way of measuring the change in, say, length or displacement relative to some initial initial length or distance. So when you hear like change, like a change in length over a length, you know that strain is dimensionless. And so what we're trying to compare with is how do distances change, how do displacements change relative to their initial location. And you can kind of see it, and I'll draw something here as kind of our starting point. This is the simplest kind of way to envision strain. And we just take a bar. And we'll say that this bar has some initial length, L naught. And we can mark a couple points on here. So we could mark a point like here and a point here. Call that point A, point B. For the sake of this discussion, we will call this the x-axis. And here's our object. We're going to take this object and apply a load to it. And I'll place it in uniaxial tension. Try to draw straight lines. Fail miserably. Pretend like that's a rectangle. And we're going to see that these points are going to move. And there's going to be two types of movement between these points. For one, point A itself is going to move. It's going to move down a little bit. And so we could kind of denote that amount of movement with a displacement. And we've talked about how we describe displacement in the x direction with the lowercase letter u, displacement in the y direction with the lowercase letter v, and displacement in the z direction with the lowercase letter w. We're going to keep that same notation here. And so this point, material point A, has displaced. We'll call that that's to its new location A prime. And it's displaced an amount u. We can do the same for our other points. So our new point B bar is going to be, or sorry, B prime. It's going to be down here. And again, you can kind of denote how much this has changed. It's also moved an amount u. Plus a little bit more. The total displacement is the one that you're familiar with. This is the one that we talked about in 305. We would say, okay, let's look at the endpoint and let's look at the new endpoint. And let's say, well, the difference between the old endpoint and the new endpoint, we'll call it delta. And what we did in 305 is we said, all we care about is the deflection of the endpoint. Who cares about what's happening in the material? We didn't consider anything about what's happening to the displacement of the objects in here. We just focused on what is happening at the end, and we'll assume that if we know what's happening at the end, we can just kind of sweep under the rug everything else that's happening in the structure. So this is what we did in 305. Is we fixated all of our attention on the end displacement of this object. Oh, I forgot to denote something here. So let's call the distance between A and B. We'll call that delta x. So the difference between our 2 points is an amount delta x. The new point A is going to displace some amount. The point B is going to displace some amount, but it's also going to displace the amount that A displaced. So it's going to be kind of like whatever A displaced plus its own displacement. So whatever A displaced plus its own displacement. And so we can write down and say, well, these points don't have to be, some finite distance apart. Right here, we're saying there's some distance delta x apart. In general, what we want is the ability to say what's happening kind of infinitesimally through this material as I slowly move from the clamped edge to the free edge. And so we can say, well, I know what's happening. I can simply compare delta U to delta X. But the fact that the initial distance between A and B is finite is just arbitrary. It just kind of makes it easier to visualize this system. And we know that whenever we have kind of a finite difference between two quantities, we can take the limit as our delta X goes to 0. And if we take the limit of delta U over delta X, as delta X goes to 0, we get a differential. And we can call that our strain in the X direction. More technically, what we would do is we would call this our strain at a point. Now, this is really not that far off from what you're familiar with, because what you're familiar with is us defining what we would call a uniform strain, which would be, let's just consider the fact that our new bar has a length L, and therefore, let's make this a little bit less ugly. Therefore, if our new bar is a length L, we could take the difference between our old bar and our initial bar, our new bar and our old bar, relative to the length of the old bar. And get a measure that looks like this. This should be familiar. This is mechanics of material definition of strain. And this is uniform strain. This is saying like, well, who cares what's happening in the material? I know that the kind of average strain at any point is basically going to be the difference of the endpoint relative to the initial length of the material. We see that when we consider what the strain at a point looks like, we end up requiring us to kind of take the limit of two material points that are really close together, which leads to a differential equation. Now you see I wrote these little d's as regular d's. That means this is an ordinary differential equation. And it's an ordinary differential equation because there's no strain in y or z as I've drawn it here. Now in reality, we know that's not true. We know that if I stretch this bar, it's going to shrink in the other dimensions. And so we would expect some displacement in y and z. And so we can kind of start to see that, like, well, the fact that this is an ordinary derivative is kind of something we're contriving here. In reality, the displacements at a particular point in the material could change in multiple directions at the same time. And so we can move from kind of uniaxial strain to what's referred to as plane strain, in which we're going to consider strain in two dimensions, x and y. And we're going to start to see how just taking the same approach into 2D lends itself to a system of differential equations, or differential relations, I guess. And so let's move to plane strain. I don't think any of this is particularly new. If you took mechanics of materials with Professor Barboni, there's a high likelihood you might have already seen this definition for strain. If not, it's not too much of a leap to go from kind of here to here. And so hopefully that's fine. We're gonna march forward into 2D strain and see if that changes things. And so in the case of plane strain, we consider a 2D slice of an object. For the sake of convenience, we will assume that this object is initially has a length of 1. So this length would be 1. And what we can do is I'm going to copy this. I'm going to make a couple of these. And we can look at how this object is going to deform as we independently stretch it in each direction. So for instance, the first thing we'll do is we'll just stretch it in the x direction. And if we just stretch it in the x direction, we would expect this kind of structure to get bigger like this. And that's our strain. This is this distance between here and here is our strain in the x direction. If we again take this length to be 1, then we can do the same thing up here. We can say, well, I'll now just stretch it in the y direction. And if that distance is 1, then this distance is my strain in y. These are what's referred to as dilational strains. There's strains that don't change the shape of the object as much as kind of uniformly or elongate it in one direction or another. A better way to define this, the idea of a dilational strain, is to say if you look at all the angles within this structure. So, if you come over here and say, hey, look, this is a right angle. After we've strained this object, all the angles remain the same. So I've got right angles in my initial square here. I make this thing a little bit bigger. I still have right angles everywhere. This is a type of strain that is kind of dilational or elongational. It's something, or sometimes called spherical. It's something that is changing. It's stretching the object or compressing the object without changing the kind of local angles between material points. These types of strains are normal strains. They result from uniaxial extension, biaxial extension, hydrostatic pressure. Alternatively, you can have a strain that is going to be distortional. Also has the term deviatoric. And in the case of something that is a distortional strain, what happens is your object in the deformed state looks like this. And here clearly you see an angle change within the material. So this angle change here is the change between here and here. We'll call gamma xy. In the case of plane strain, we are assuming that strain in the z direction, the shear strain in the xz, and the shear strain in yz are all 0. So in the case of plane strain, these are the 3 things you can do. You can elongate it in x, elongate it in y, or distort it. And distorting it would cause an angle change in the xy plane. And so how do we take this diagram up here and repeat it for these types of deformations? And what we want to do is we want to do it kind of in general. And so what we're going to do is we're going to separate it into your kind of elongational strains and your distortional strains, or your normal strains and your shear strains. And so we'll start with the normal strains first, and we'll say, okay, well, let's blow this diagram up a bit. Again, x and y. I will again draw my structure here. We can label all these points. So label this thing A, B, C, and D. And we can imagine that some combination of stresses distorts these material points. These are, you should think of these are material points within a body. Like imagine you took a sheet of rubber, like a thin sheet of rubber, kind of like a sheet of paper, but something that's really easy to stretch, really like a soft rubbery sheet. And you drew A, B, C, and D on this sheet of rubber, and then you stretched it in 2 directions. And the question is, where do those material points go on that stretched sheet of rubber? And how do we relate where they are in their deformed state to where they are in their original state? Does everyone understand that? That's what we're doing right now. In the case of plane stress, imagine a sheet of rubber, 4 dots demarking a square on there. You're going to stretch it equally, or maybe not. You're going to stretch it in 2 directions, x and y. Those material points are going to move somewhere. Like literally the marker points you put on your rubber sheet are going to be in a different spot in space after you stretch it. So they might look like this. And now they inhabit 4 new places. We'll call them A prime, B prime, C prime, and D prime. And what we want to understand is, how do these material points move? Since the area of these squares is not the same, but the angles are, this isn't just a translation. We didn't just take my rubber sheet and move it over here. We took our rubber sheet and we stretched it, keeping the angles fixed, so just stretching it in x and y, no shear. And the material points ended up in a new location. And now we're tasked with trying to figure out how these things move. And we do the same thing. We say, okay, well, like, let's look, point A, it moved the distance V. Remember, V is our displacement in the y direction. That's the y direction. It moved a distance v, and point A moved a distance u in the x direction. We can get a little bit more careful here, and we can say, well, again, we're going to think in terms of some finite distance. So we'll say this is a distance delta x. And this is a distance delta y. So the challenge and where things get tricky is when you look at points B and point B prime and D prime. Because what's happening with B prime and D prime is the exact same thing that's happening up here. It's going to move a distance u plus some change in u relative to the x-axis. We didn't really say that here because we only cared about the x-axis. But down here, we care about x and y. And so what that means is that this point is moving a distance u, because A moved, plus some change in u. Now that change in u is relative to the distance to a change in x. How much did u change as you moved along the x-axis? So relative to an increment in x, how much did our displacement change? Now that's not a, oops, I should have made these, I should have skipped a step here. I guess I don't, all right. Sorry, I'm going to erase something here and say, oh, that's not erase. I'm going to say, instead of us going through the limit, we've already done the limit. We understand that as you take the limit, it goes down. We'll call this a small d, x and a small dy. This is just our way of not having to show that the limit of delta x is delta x goes to 0, or the limit of our strain is delta x goes to 0, takes us to a differential. We know that, so we're going to use these elements dx and dy. So in that case, what we're asking when we look at b prime relative to b is, okay, it moved an amount u, and it also moved some amount delta u or du relative to a change in x, so du by dx. Now this is not a dimensionally consistent statement, because u is a displacement, du dx is a strain, or if it's not a strain, it's certainly a dimensionless thing. It's a strain over, it's a displacement over a distance. That's a dimensionless object. And so what we're actually saying is we want to know how much u changed as we moved along x. So the change in u relative to the change in x over a distance dx. And so what we do is we take this thing and we multiply it by a distance dx. Take a second and write down this displacement, displacement here. hopefully, at least by pattern recognition, you saw that this is probably going to be something like V plus dV dy times dy. You might be asking yourself, like, why is it the derivative of V with respect to y times, like, why is there a first derivative term there? It's the exact same reason this appeared for our derivation of the stress tensor. You can think of this as nothing more than a Taylor series expansion, in which we say we're going to truncate at the first order term. We're going to say, okay, there's some displacement, and if I go to the next order, there's a change in displacement relative to its to one distance x times dx. So it's kind of your f prime over 1 factorial times the actual distance that you moved. This is the same thing. It's a Taylor series expansion. That's all it is. It's just expanding around a point and trying to capture the displacements if we go to our first order in our Taylor series expansion. So let's look here. Strain is going to be the change in length relative to the initial length here. So we can pretty clearly see that our u's are going to go away. Well, we can write this out. Let's write this out. We can say I have, let's see if we can do this right. Our new length is u plus delta u, delta x dx, minus our old length, which is dx. Oops, that's not right. Give me a second here to think. So the original length is dx. Sorry, I'm thinking on my feet here. The new length is dx. Yeah, I think this is right. And then we end up with delta u, delta x. So local line. So the strain in the x direction just consists of the relative change in u with respect to x. We're just taking, you're kind of like taking away any relative translation between the points. So this kind of u minus u, and you're just looking at kind of how these 2 points stretch relative to each other. From the same logic, you can get the strain in y to be delta v, delta y. And if we know that our strain tensor, is going to have this, and we know that, let's see here, these terms are all 0, 0, 0, 0, 0, 0. Plane strain only cares about strain in the XY plane. We've now just found two of them. And so we only have one left. You might not be able to see that. There we go. So not bad. From geometry, we've got two of the three strain tensors, strain components of our strain tensor. And we just have to do the same thing, but for a distortional strain. So let's clear this off. And now let's consider a strain that does change the angles between ADB and CDB. And so let's see if I can draw this without too much pain here. Let's see. Here again, we have our new points, A prime, B prime, C prime, and D prime. And I'm going to highlight here the fact that there are different amounts of angular change, at least in how I've drawn it, between B prime and A prime and D prime and D. But sure, D prime and A prime, sorry. Okay, so we can call both of these things different angles here. We can say, well, this will be an angle, this is a negative rotation, right? This is clockwise, so this is going to be like some negative. We'll call it an angle alpha y. And this one is counterclockwise, so that one should be positive. So we'll call this one alpha, we'll call it alpha x. So the question is, what are these angles? And we can kind of start to see that this distance, let's pick a different color here, this distance, now I'm purposely drawing a straight line there as opposed to an angle, a curved line like the purple one. And they purposely both kind of look the same, because we're going to say in the limit of small strains that distance, this is a small angle approximation we can make, and that distance, we know that distance, and we're going to say that distance is going to be dv dx, because now what we've done is we've said, well, let's consider, look, over here we said, we really want to know what's happening as we move along, as we displace in the x direction relative to the x direction. And here I'm drawing this red arrow that's saying, we really want to know how much we've moved in the y direction relative to some change in the x direction. Technically, this angle is really like something like, we know this angle, it's like the tangent of some amount that we've moved here. But in the limit of a small strain where the difference between the difference in length between A and B and A prime and B prime is really small, then this angle can be approximated just as we would in a small strain case as simply this distance dV dx. Change in V relative to a change in X over a distance dx. And here we have the same thing. We can say change in U, because we're moving in the X direction, relative to a change in Y over a distance dy. Same idea. We have in the thing I'm trying to highlight here is in the normal strains, where we're looking at something that doesn't change angles, what we care about is how much did our displacement vector change in the direction that we're moving in over some distance? How much did our displacement vector change in the direction where it's moving relative to some distance? And here we're doing the opposite. We're saying how much did our displacement vector in the vertical direction change as we moved a horizontal direction dx. And that's what this is trying to say. How much did our displacement change in the horizontal direction as we moved a vertical distance dy? And that means we can write our alpha x as dv dx and negative alpha y as du dy. And what we're interested in here is the total angular change. What we're interested in here is to say, I have some angle. Oops. I have some angle that it can be described by the points DAB. So if I go from DAB to D prime, A prime, B prime, that angular change as you go from whatever the initial angle between the two material points were to the new angle between those material points, that's our shear strain. It's denoted by gamma xy, and it's equal to the difference between alpha x and alpha y, which is equal to partial derivative of u with respect to y plus partial derivative of v with respect to x. And that plus sign appears because of this negative alpha here, which was due to the fact that this was a clockwise rotation. This is a counterclockwise rotation. I think there's always a little bit of confusion in terms of what denotes a positive shear strain and what denotes a negative shear strain. Typically, if you're going from something like this to something like this, that's positive. And if you're going from something like this to something like this, that's negative. I've always found these distinctions to be, I don't want to say arbitrary, but you know, shear is different than tension and compression. Shearing something to the left or right is not as distinctly different as stretching versus pushing or compressing something. So it seems like we're done, but we're not quite done. Some of you might have noticed this weird difference in notation that I'm using, which is that in my strain tensor, which is epsilon, I have epsilon xy, and down here, what we've solved for is something we're calling gamma xy. We're going to resolve this in a minute. We're going to try to connect gamma and epsilon. They seem like they should be the same for mathematical reasons and kind of simple, compact ways to write things. We have this like slight difference that we have to account for. It's basically a factor of a half that pops in, and you'll see why in a second. But let's take a break until like 10:02, 10:03, and we'll come back and move to 3D and resolve this difference, and then we'll talk for the remainder of the lecture about large strains. And if you have any questions, you can ask them now or think of them and ask them when we come back from break. So let's take a few minutes. All right. Let's return to this messy business of geometry. We've kind of done the same thing we did when we were talking about stress. We started with 1D, we moved on to a plane stress, and then we said, well, you can probably guess what's going to happen as we move to 3D. There's just kind of some pattern recognition here. We can draw out the free body diagrams if we want, or we can draw out these geometries of cubes and parallelepipeds if we want. But also you could just say, well, I don't know, I could probably guess that the strain in the z direction is going to be the relative change in W with respect to the relative change in Z. And I can probably guess that I'm going to have two other shear strains that are going to be the other combinations of U and W, V and W for Y, X, and Z. So let's do exactly that. Let's now that you've seen how this derivation works in 2D, I don't think it's going to come to a surprise to you that if our strain in the X direction is the relative displacement in the X direction relative to a change in X, the strain in the Y direction is the relative displacement in the Y direction with respect to a change in Y, that our strain in the Z direction is going to be the relative displacement in the Z direction relative to a change in Z. Similarly, we know that gamma xy is du dy plus dv dx. If that's the case, then gamma, go with yz. Is going to be dv. Now that v corresponds to displacement in y, and that's got to be relative to a change in z because we're in gamma z, gamma yz. And we have to add to that a change in z, which is going to be dw relative to a change in y. And finally, gamma xz du dz plus dw dx. These are all the components of strain. These are the 6 components of strain. We have this lingering problem, which is that these are written in terms of gammas, and these are written in terms of epsilons. And the only reason that's a problem is because we would like to be able to stick all these things into a tensor called epsilon. That's our strain tensor. We'd like to relate our strain tensor epsilon to our stress tensor sigma using a constitutive model. And these aren't epsilons. And so what do we do? Well, the short answer is we say that our epsilons are equal to 1/2 of our gammas. And I could tell you why, but it basically has to come back to a shorthand way of writing notation. And so, and the reason why this is important is because everyone's always going to write epsilon xy, epsilon yz, epsilon xz, and you need to know that epsilon xy is equal to 1/2 of gamma xy. Epsilon yz is equal to 1/2 gamma yz, and epsilon xz is equal to 1/2 of gamma xz. And this really comes down to our ability to write this in a compact way. And so what I mean by writing this in a compact way is instead of keeping track of a stress tensor that looks like this, Probably didn't leave myself enough room here. So those are my normal strains. And my shear strains look like 1/2 du dy dv dx and 1/2 du dz. And what's this one? This one's going to be the other one. 1/2 dv dz dw dy. And I'll just remind you that this is symmetric with this one. This is symmetric with this one. And this is symmetric with the other one. I'll move the other strains just so they look like they're in the right spots. There we go. There we go. So that's our strain tensor. It's hard to do math with an object like this. It's a big matrix. It's hard to do pen and paper calculations with these types of things, and so you'll rarely see it written this way. What you'll see it written as is one of two different ways. So where does this 1/2 come from? Well, the 1/2 comes from the fact that we can write our strain tensor like this. Epsilon ij is equal to 1/2 the partial derivative of ui with respect to xj plus partial derivative of uj with respect to xi. Again, this pesky notation, this indicial notation. If you don't like this notation, and I'm going to try to unpack this for you in a second. If you don't like this notation, you prefer the direct notation that you see in like a multivariate type class. Another way to write this exact same thing is to say that our strain tensor is equal to 1/2 the gradient of our displacement plus the transpose of the gradient of displacement. You'll hear terms like a strain gradient. You'll hear terms about displacement gradients. Clearly, we have something that's like a displacement gradient here. A gradient is like derivatives of your thing with respect to spatial distances. And so we have stuff that's like derivatives of our displacement with respect to spatial distances. We get a gradient of our displacements. These are two shorthand ways to write that big box of colored stuff over there. They require some unpacking. So what on earth do I do with this thing? I don't even know what I don't even know what UI means. And I'm just telling you this so you can see it, but you'll see people writing that U is UX, V is UY, and W is UZ. And what do I do with this stuff? This stuff isn't helping me either, in which I have X comma X sub J, X sub I. I don't know what that means. Well, what that means is people will say, well, X, we'll write X as equal to X sub X, Y as equal to Y, that means X sub Y, and z is equal to x sub z. And this actually isn't even the end of it, because what people really are doing here is they're saying, well, instead of using x, y, and z, why don't I use 1, 2, and 3? Because then it's easy for me to say, oh, just sum over numbers instead of summing over letters. x1, x2, x3. You might be thinking this seems like a lot of annoying ways to keep track of different letters and different combinations of stuff, and I sympathize with you. I will say the benefit of these types of things has to do with the fact that you are often trying to handle equations either switching between coordinate systems or in one particular coordinate system, but then you want the results to be general for other coordinate systems. And so you don't want to have your strain tensor defined in Cartesian space if you're going to be working on problems that have to do with contact lenses in which you're on a spherical surface, and the Cartesian is not really helping you do anything there. So I empathize with how misleading and ugly these types of things look like, but let me just show you what this means. So say I want to calculate the strain in the XX direction. Well, what does that mean? It means I put in I is equal to x and j is equal to x. So it means I say I have an equation that looks like 1/2 partial derivative of u x with respect to xx plus the partial derivative of ux times the partial derivative of xx, which is equal to, based on what we have written in here in blue and orange, that's equal to 1/2 partial derivative of u with respect to x plus the partial derivative of u with respect to x. And if I take du dx plus du dx, I get 2 du dx. That's not the strain. That's twice the strain, so I take half of that. So that's my strain in the x direction. Let's do it for another one. Let's do, I don't know. Let's do one of the weird ones that we haven't done yet. Let's do yz. So it's going to be 1/2 as the partial derivative of u. Now the I is replaced with the letter y, so that's u sub y. And the j is replaced with the letter z, so we're going to be dx z plus du z dxy. Now let's go to our chart over here, and we would say, okay, du sub y is equal to v, so that's dv. And x sub z is equal to z, so that's just going to be dv dz. And we're going to add to that uz, which is w, and dx sub y is y. And here's where you'll notice where the gamma epsilon thing comes in. Because look, this, oops, I didn't want to do that. This is this. But in order to make the math work out for all the components of the strain tensor, we have to have this extra 1/2 in there. Remember, because if we didn't have the 1/2 in there, then our normal strains would have been wrong. We would have had twice the amount of normal strains. So we have a 1/2 in here. So this is equal to 1/2 gamma x, oops, no, gamma yz. Does this notation make sense now? Does seeing it like this help? Like, that's the idea, is that I have one equation that I can unpack to whatever strain I want. It actually gets worse because people don't like writing things with partial derivatives like that. So no one actually does that. What they do is they say, let's introduce one more rule. And we'll say that I'm going to write that ui comma j is equal to the partial derivative of ui with respect to xj. Okay, what does that do for us? Well, that makes this notation even more compact, because now I can say that epsilon ij is just equal to 1/2 ui comma j plus uj comma I. Your normal strains, oh gosh. Normal strains are when I is equal to j, and your shearing strains are when I is not equal to j. How are we doing? Have I lost you in a sea of indices, or is this making sense? These are the two ways you will encounter your strain definitions. These things here are linear or small strains. And there's just two ways of writing them: direct notation and indicial notation. It's just like there were with stresses. In stresses, we wrote the divergence of the stress tensor. So we wrote, so if we were to talk about stress, we would say divergence of stress is equal to, oh no, we'll put the body force in there. Plus your body force is equal to 0. And in indicial notation, we would say that sigma ij comma j plus fi equals 0. Questions? I don't know how much of this is stuff you've seen before, or stuff that makes sense, or stuff that you're completely lost on. So let me know. I guess I mostly want you to take away a couple of things from this. One of the things I want you to take away is that just like stress, strain is a tensor. It has 9 components, 6 of them are unique. Just like stress, 9 components, 6 of them are unique. I want you to know this. And then I want you to be aware of the fact that if you pick up an engineering textbook, there's a very high likelihood that you won't see things written out in this, what's referred to as component notation, where you write out every single explicit component of each strain tensor. What you will more commonly see, depending on the textbook, is either this or this. And I want you to, at the very least, say if you run across this equation in the textbook, you're like, oh God, okay, I know what that means. Those indices mean something. I can go look that up, but I know that that's telling me how to calculate my strain tensor. And I know that my strain tensor is some measure of displacements in a direction relative to derivatives in the 3 cardinal directions. That's kind of the takeaways that I want you to have. The minor details of how the initial notation works is not important for you at this point. If it is, you can look it up. I want you to know that these strains are linear, and I want you to be able to immediately tell that they're linear. And the way to immediately tell that they're linear is the fact that in either of those boxed equations, U appears to first order. There's nothing that's like U times U, U squared, some crazy thing of U. It's just derivatives don't make something nonlinear. I think this can throw people off. Derivatives and differential equations make things hard, but they don't make things nonlinear. It's the product, it's literally like the squaring of the thing that makes something nonlinear. So in this case here, you just have a linear strain because you have changes in displacement plus changes in displacement. There's nothing nonlinear about that. I want you to be able to recognize that these equations are linear. I will now show you what the nonlinear strain form looks like. This is not something we're going to use. You're not going to have any homework or exams on this next part. There's not going to be anything that you're going to encounter on this, except that if you go off and do finite element analysis for some company after you graduate or you go to graduate school, you will certainly hear these terms. You will certainly hear about the deformation gradient and Euler-Lagrange or Green-Lagrange strain tensors. And you will certainly see it written not in terms of derivatives of displacement, but maybe in terms of the deformation gradient. And I don't want you to be like, what on earth is that? It doesn't look like anything like Professor Holmes said. So let me take a few minutes, the remainder of class, to show you what the nonlinear strains look like. This is like, write it down if you want, or just kind of follow along if you can. But this is mainly for what I think will be beneficial for you in the future. So more often than not, the way people talk about nonlinear deformations, this is absolutely true for problems in biological biomechanics of growth. It's absolutely true with like studying of hyperelastic materials, things like rubbers. And what you typically think of is, okay, I have some, and these things can take on a bunch of different terms. I have some reference or undeformed configuration. And my undeformed configuration might have a material point, which has got some vector, and this is going to be capital X. This is my reference. You might see this a bunch of different ways. Reference, initial, undeformed configuration. And then you're going to do something to it, and it's going to be a deformed. And all your displacement vectors are going to be marked by a lowercase x. I want to put some flags on my uppercase x to make it look like an uppercase x. And this might be called your deformed configuration or your current configuration. And the deformation gradient is exactly that. It's a gradient of how things deformed when you go from, when you map for your material points from big X to little x. And so the deformation gradient which is also a tensor, is going to be a tensor given by Fij, which is equal to little x I comma j. And now we know what that means. Little x I comma j means take the partial derivative of little x I with respect to, now in this case, we're taking it with respect to the partial derivative of big X j. Now you could just stick in for I and j 1, 2, or 3, and you're going to get a tensor. So for instance, I could write dxi, sorry, dx1, 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 dx2, dx1, dx3, and so on. I could say dx2, d big X1, d little x3, d big X1, and then down the middle here is going to be our and the last two are what? It's going to be dx2, d big X3, dx3, d big X2. So that's the deformation gradient. Okay, so we've got this deformed configuration, we've got this reference configuration, initial configuration. A displacement of my material point is going to be the difference in X and big X. So that means I can write displacement as my displacement vector U. This is going to be a vector that will include, U is going to be like U, V, and W. So it's kind of got all of them wrapped in there. So this is my displacement vector, which has got 3 components in all the directions. And it's just going to be the difference between my deformed configuration, little x, which is a vector, and my initial configuration, big X. If you want to write this in initial notation, you would write UI is equal to xi minus big X I. You can simply take this equation and solve for the displacement vector in your deformed configuration. Usually that's what you want. You got some initial configuration, you do something to it, you want to know what happened. So you can solve for little x, just literally moving big X to the other side of the equation. You would write that U minus big X. And then we can think about how our definition of our displacement of our deformation gradient was take the derivative of x with respect to big X. And we can do that here now, but now we have a definition for x that's written in terms of displacement. So for instance, I could write this as, so if I want to calculate f, I could say f is going to be the derivative of my stuff with respect to big X. And my stuff is what? Did I solve for that wrong? I feel like I did. Oh yeah, I totally did. This is a plus, isn't it? This is going to be U plus big X. Really, I'm just taking this thing here. Oops, I should circle it a different color. I'm just taking this thing here and sticking it in, just like we have up here. And what happens when you do that? Well, you get something that looks sort of like this. You get something that's like du dx plus dx. And what on earth is dx? That seems like that should simplify out. It looks like it should be 1. It's actually not 1. It's because these are vectors, it's actually the identity matrix or Kroneker's delta. If you're living in direct notation, you would say that this, whoa. If you're living in direct notation land, you would say that this is capital I. And if you're living in additional notation land, you would say that this is Kroneker's delta, which is either written like this or like this. Whoa. Wow. But basically, it's a matrix of 1s on the diagonal and 0s everywhere else. Okay. So this is, we would write in additional direct notation, we would say du dx plus I, or Fij is equal to Kroneker's delta dij plus ui comma j. Okay. The most common, there's many very different and annoying ways to measure strain. The most common ways you measure strain are with what's referred to as the Green-Lagrange strain tensor or the Green-Finite strain tensor. And well, let's write that in green. Why not? So we'll go with Green-Lagrange. And it looks like this. It looks like epsilon, the tensor strain, the strain tensor epsilon, is 1/2 of my displacement gradient, the transpose of my displacement gradient, times my displacement gradient minus I. Or in additional notation, this looks like 1/2 FKI, FKJ. I find this calculation to be easier to do in additional notation because my brain kind of craps out when I think about direct notation. So we're going to do it in this one on the right here. So all I need to do is take this thing and insert it here with the appropriate change of letters. And so I would say that my Green-Finite strain tensor looks like, let's do this with a square bracket. It's going to look like delta ki plus uk comma I. And then it'll be delta
Okay, J, there'll be a payoff here, I promise. It'll be like, oh yeah, that looks kind of like the other thing. This, and then we have to take away a ij. We can FOIL this thing out. And delta ki, delta kj, plus delta ki ukj plus uk comma I delta kj plus uk comma I uk comma j minus delta ij.
Now, this is why I said don't worry. There's going to be a payoff here. If the math is throwing you, that's fine. You don't know how to do this stuff, especially what I'm about to do, which is to say that the result of multiplying two tensors like this, in which you have k appearing in both of them, is that this is kind of the power of tensor and additional notation, is that this thing just contracts and becomes delta ij. If you're interested, happy to explain how all this graph works, but it does. And that's lovely because that means this term and this term cancel out. They're both delta ij. Now, what do all these other deltas do? Well, the delta basically serves as like a way to change letters in your equation. I mean, it does more than that, but for right now, we're going to just say it like that. So that means this is going to take, this thing basically says take Kroneker's delta here is saying take the k and the term that it's multiplying and change it to, so this term has a k, this term has a k, change the k and the u to an I because of this I. Again, I don't expect you to know this. I'm just kind of showing you because once we get to something, it's going to look sort of familiar. And so this becomes u I comma j, and this, because of k, k, and j, becomes u j comma I. And that last term doesn't change. And so finally, the Green-Lagrange strain tensor looks like this. Ui comma j plus uj comma I plus uk comma I, oops, uk comma j. Why do we do all this and how does this relate to anything we've talked about so far? Well, hey, look. These are my linear strains that we already had. This is the exact stuff that we wrote up here. And we're just adding to that a nonlinear term. How do I know this is nonlinear? I see u appearing twice in that term. U, derivatives of u multiplied by derivatives of u, that's nonlinear. I have squared my u's. So my Green-Lagrange strain, which is my most common form of the nonlinear strain tensor, consists of the linear part, which you already know, we've already derived, plus a nonlinear part. And if you want to write this in direct notation, I'm going to skip the derivation and tell you that in direct notation, this becomes equal to gradient of u plus transpose of the gradient of u plus
You could probably guess what the next two terms are by pattern recognition. It's got to have a u appearing twice. And what you might recall from linear algebra is that if you're going to be multiplying these two things, one's a row, one's a column vector, they need to give you a tensor. So you're going to end up with something that's like grad u transpose grad u. Again, I don't expect you to know how to derive this or know how to even use these, because using them is not easy. What I do expect you to know is that if you see a strain tensor like this, in which you see u appearing twice in the same term, this is a nonlinear strain tensor. That's the main thing I would like you to be aware of. And the nonlinear strain tensors come from a discussion of your deformation gradient. And that is the most common way you'll encounter a lot of these things in finite element analysis, is through the concept of a deformation gradient. And the reason why you see it in terms of a deformation gradient is primarily because it's easier to handle nonlinearity when talking about it in terms of this different displacement gradient or deformation gradient. So I'm showing you this so that terms like deformed configuration, reference configuration, initial configuration are not totally out of left field for you. I'm showing you this because if you hear terms like the Green-Lagrange or Green-Lagrange strain tensor, you should think, oh, that's nonlinear. Okay. And if you don't know, at the very least, you should be able to look at an equation like this one or like this one and say, okay, the first term just got a u in it. Just got a u in it. U times u. This is nonlinear. U times u. This is nonlinear. I want you to be able to at least identify that these are nonlinear ways of describing deformations. That's all I have for you today. The last part was just for fun. I have a bizarre sense of fun. Thanks, everyone, and see you all on Thursday.